Hey everyone, welcome back to the channel. Today, we're diving into something that's not about gears, gadgets, or glitter bombs. It's the invisible framework that holds our entire profession together. The stuff that makes sure the amazing things we build actually help people and don't, accidentally cause a robot apocalypse. It's what separates a true professional from just a tinkerer. I'm talking about the bedrock of our work ethics. It might not sound as exciting as launching a pumpkin with a trebuchet, but trust me, without it, none of the cool stuff would be possible or safe. So, what are these rules of the road for engineers? Well, several professional organizations like the American Society of Mechanical Engineers have laid out these core tenets. Think of it like a universal code of conduct. We're going to break down what I like to call the universal ethical principles for mechanical engineering and its related subfields. These aren't just suggestions. They are the fundamental promises we make to society. They ensure that when we design a bridge, a medical device, or even a simple toy, we're putting people first. This is super important because the work we do has real-world consequences. A small miscalculation or a decision to cut a corner can have massive impacts on people's lives, their safety, and the health of our planet. So stick with me as we go through the 9 core principles that every single engineer, from a fresh graduate to a seasoned pro, needs to live and breathe every single day. Let's get into it. All right. Kicking things off with the absolute non-negotiable #1 rule of Engineering Club, the health, safety, and welfare of the public shall be held paramount. This is our prime directive. Before we even think about efficiency, cost, or how cool something looks, we have to ask the most important question. Is this safe? It's the oath we take, whether we say it out loud or not. Every line on a blueprint, every material we select, every calculation we run, must be filtered through this lens. It's our fundamental duty to society. This means we are the last line of defense against potential disaster. When you design a new braking system for a car, you're not just assembling parts. You're responsible for the family that will rely on that system in an emergency. When you're working on the structural integrity of a building, you're not just crunching numbers. You're protecting every single person who will walk through its doors for the next 100 years. This principle demands that we anticipate potential failures, design redundancies, and never, ever cut corners on safety for the sake of a deadline or a budget. Think about the classic engineering case studies, the ones that unfortunately end in tragedy. The Hyatt Regency walkway collapse, the Challenger space shuttle disaster, the Tacoma Narrows Bridge. These weren't just physics problems, they were failures of this primary ethical duty. Engineers in those situations either overlooked, were pressured to ignore, or failed to adequately communicate the risks. This principle means having the courage to speak up, to say no, this isn't safe enough, even when it's the unpopular opinion. The public trusts us with their lives, and that trust is built on this single paramount commitment. It also extends beyond just preventing immediate physical harm. We have to consider the long-term welfare of the public. Does this product create hazardous waste? Does this manufacturing process pollute the local water supply? Will this automated system displace an entire workforce without a plan for their future? These are all questions that fall under the umbrella of public welfare. It's a massive responsibility, requiring us to think like engineers, but also like sociologists, environmentalists, and ethicists. We have to see the bigger picture of how our creations fit into the fabric of society. Ultimately, this principle is about recognizing the power we hold. We have the knowledge and the skills to shape the world in profound ways. With that power comes the immense responsibility to wield it for the public good. Every other principle we're going to talk about today really just supports this one main goal. If you remember nothing else, remember this. Your primary job as an engineer is to be a guardian of public safety. Everything else is secondary. Next up is a principle that sounds simple, but is the glue that holds all our professional relationships together: honesty and integrity. This means we have to be truthful in everything we do. It's about being upfront in our reports, our statements, and our professional testimony. If a test result isn't what you hoped for, you report the actual result. You don't fudge the numbers to make the project look better. Your reputation as an engineer is your most valuable asset, and it's built entirely on a foundation of trust. Once that's gone, it's almost impossible to get back. This principle covers more than just not lying. It's about intellectual honesty. A huge part of this is giving credit where credit is due. Engineering is a team sport. We're constantly building on the work of others. If you use someone else's code, a colleague's design idea, or data from a published paper, you acknowledge that. Claiming someone else's work as your own isn't just unethical, it's theft. It's also about being honest about your own capabilities. Don't promise you can deliver a project on a timeline you know is impossible, or claim expertise in an area where you're just a novice. Furthermore, we must avoid all deceptive acts. This can be subtle. It could mean not selectively presenting data to support a desired conclusion while hiding the data that contradicts it. It could mean being transparent about conflicts of interest. For example, if you are asked to review a product from a company that your brother-in-law works for, or a company you own stock in, you have a duty to disclose that potential conflict. Integrity means ensuring that your professional judgment isn't clouded by personal relationships or financial incentives. Your loyalty must be to the truth and to the project's best interest. Think about the consequences when this principle is violated. The Volkswagen emissions scandal is a perfect example. Engineers deliberately designed software to cheat on emissions tests. This was a monumental breach of public trust, a calculated act of deception that had huge financial and environmental consequences. It tarnished the reputation of countless honest engineers and the company as a whole. This shows that a lack of integrity doesn't just hurt one project, it can undermine the public's faith in our entire profession. We have a collective responsibility to police ourselves and maintain this standard. So at its core, this principle is about building a culture of trust. Your colleagues need to trust you, your clients need to trust you, and most importantly, the public needs to trust you. This means being a straight shooter, communicating openly, admitting when you've made a mistake, and always acting with honor. It's about doing the right thing, especially when no one is watching. That is the true measure of integrity. Principle number 3 is all about knowing your stuff, but also knowing the limits of what you know. It's the principle of competence. This means that as engineers, we should only take on work that we are qualified to perform, based on our education and experience. Just because you're a brilliant mechanical engineer who specializes in thermodynamics doesn't mean you should sign off on the structural plans for a skyscraper. It's about having the humility and self-awareness to recognize the boundaries of your own expertise. This principle is a direct extension of our duty to protect the public. An incompetent engineer is a dangerous engineer. If you venture into an area where you lack the proper knowledge, you're not just risking your career, you're risking people's safety. Imagine a mechanical engineer with no background in biocompatible materials designing a new artificial heart valve. The potential for catastrophic failure is enormous. Being competent means knowing when to say, "This is outside my area of expertise, you need to consult a specialist." It's a sign of strength, not weakness. But competence isn't a one-and-done deal. You don't just graduate from college and you're competent for life. Technology, materials, software, and regulations are constantly evolving. This is where the second part of this principle comes in, the commitment to continuously update your knowledge and skills. It's a duty to engage in lifelong learning. This could mean taking professional development courses, attending conferences, reading technical journals, or getting certified in a new area. The field of engineering waits for no one, and what was state-of-the-art 5 years ago might be obsolete today. Think about the rise of fields like additive manufacturing, or three-dimensional printing, or machine learning in mechanical design. An engineer who graduated 20 years ago would have had no exposure to these in college. To remain competent and effective, they have a professional obligation to learn about these new tools and how they can be applied safely and effectively. Resting on your laurels is not an option in this profession. You have to stay curious, stay engaged, and keep sharpening your skills throughout your entire career. So, competence is a two-sided coin. On one side, it's about having the discipline to practice only in the fields where you have proven expertise. On the other side, it's about having the drive to constantly expand and update that expertise. It's about ensuring that when you put your name and your professional stamp on a project, it signifies a guarantee of quality, knowledge, and skill. It's a promise to your client and to the public that the job has been done right by someone who knows what they're doing. This brings us to our fourth principle, objectivity and impartiality. This is, honestly, the scientific soul of engineering. What it means is that our decisions, our analysis, and our conclusions need to be based on facts, data, and sound engineering principles. We really have to be like a judge, weighing the evidence dispassionately to arrive at the correct verdict. Our work should be free from the influence of personal feelings, biases, or, external pressures. The numbers don't lie, and our job is to interpret them without prejudice. But let's be real, this can be harder than it sounds. We all have biases, both conscious and unconscious. Maybe you have a preference for a certain supplier, or a loyalty to a particular design you came up with, or even a desire to please a manager who's pushing for a specific outcome. Objectivity requires us to actively fight against these influences. It means running the tests, analyzing all the data, and letting the results guide the decision, even if it's not the outcome we personally wanted. It's about putting the integrity of the engineering process ahead of personal gain or ego. Impartiality also means resisting external pressures. A client might pressure you to approve a cheaper, lower quality material to save money. A sales team might push you to sign off on a product's capabilities before testing is complete just to meet a launch date. A politician could try to pressure you to endorse a public works project for political reasons. In all these cases, the ethical engineer must stand firm. Our professional judgment cannot be for sale. We serve the truth and the safety of the public, not the agenda of the person paying the bill. Consider a scenario where two different design options are on the table. One is a conventional design you're very comfortable with. The other is a novel, innovative approach proposed by a junior colleague. An objective engineer would evaluate both options using the exact same criteria: performance, cost, safety, manufacturability. They wouldn't just dismiss the new idea because it's unfamiliar, and they wouldn't favor their own idea out of pride. Instead, they would conduct a fair, data-driven comparison and choose the option that is demonstrably better for the project, regardless of its origin. Ultimately, objectivity and impartiality are what make engineering a trusted profession. People rely on us to be the source of factual, unbiased information. When we provide an expert opinion, it's expected to be based on our technical knowledge, not on who we like or what we stand to gain. By stripping away bias and pressure and focusing solely on the data and the physics, we make sure that our decisions are robust, defensible, and truly in the best interest of everyone the project will affect. All right, let's talk about principle number 5, which is all about secrets and ideas. This is the principle of confidentiality and intellectual property. In our line of work, we are often entrusted with sensitive information. This could be a company's secret formula for a new material, the design for a yet-to-be-released product, or proprietary manufacturing processes. This principle dictates that we have a solemn duty to protect this information and not disclose it without consent. It's really the engineering equivalent of doctor-patient or attorney-client privilege. This confidentiality is absolutely crucial for business. Companies invest millions of dollars in research and development to gain a competitive edge. If their engineers were to casually discuss these trade secrets with friends, post them online, or take them to a new job at a rival company, it could be devastating. This ethical obligation is often reinforced by legal agreements like non-disclosure agreements, or NDAs. But the professional duty exists even without a signed piece of paper. It's a matter of professional respect and trustworthiness. You are a guardian of your employer's or client's sensitive information. Now, the other side of this coin is respecting the intellectual property, IP, of others. Intellectual property includes things like patents, copyrights, and trademarks. As engineers, we must not use pirated software or knowingly infringe on someone else's patent. When we are designing a new product, we have a responsibility to do our due diligence and make sure we're not stealing an idea that someone else has legally protected. This protects the spirit of innovation. If people and companies can't be sure their new ideas will be protected, there's just less incentive to invest the time and money to create them in the first place. Think about it this way. Patents and copyrights are the mechanism society uses to reward innovation. They grant the creator a temporary monopoly on their idea as a reward for sharing it publicly. By respecting these systems, we contribute to a healthy ecosystem where new ideas can flourish. It means if you come across a patented mechanism during your research, you don't just copy it. You either design around it, license the technology from the patent holder, or wait for the patent to expire. It's about playing by the rules of the creative game. So this principle is a balancing act. On one hand, you must be a vault for the confidential information of your own company or client. On the other hand, you must be a respectful citizen in the broader community of ideas, honoring the intellectual property rights of others. It's about creating an environment of trust and fairness, where companies feel safe sharing their secrets with their engineers, and innovators feel safe sharing their inventions with the world. This, in turn, fosters the competition and collaboration that drives our entire field forward. Now for a principle that has become more and more critical in the 21st century, environmental stewardship and sustainability. This is the recognition that we don't engineer in a vacuum. Everything we design, build, and operate has an impact on the planet. This principle calls on us to be responsible stewards of our environment. It's not enough for a design to be safe and functional. It must also be as environmentally friendly as possible. We have to think like a part of nature, not apart from it. This means considering the entire life cycle of a product. It's called life cycle analysis. We have to think about the environmental cost of extracting the raw materials, the pollution generated during manufacturing, the energy the product consumes during its useful life, and finally, what happens to it at the end of its life. Can it be recycled? Is it biodegradable? Or will it just sit in a landfill for 1,000 years? A truly elegant engineering solution is one that addresses all of these stages with minimal environmental harm. Sustainability is the key concept here. The formal definition is meeting the needs of the present without compromising the ability of future generations to meet their own needs. For engineers, this means designing things that are efficient, that use renewable resources where possible, and that minimize waste. It's about designing cars with better fuel economy, creating buildings that require less energy to heat and cool, developing manufacturing processes that use less water, and creating products that are built to last, not to be thrown away. This is a massive paradigm shift from the engineering of the past, which honestly often prioritized performance and cost above all else. Today, the environment is a primary design constraint, right up there with safety and budget. This has led to incredible innovation in areas like renewable energy, wind turbines, solar panels, electric vehicles, green building materials, and the circular economy, where products are designed from the start to be reused and recycled. It's a challenge, but it's also one of the most exciting and important areas of modern engineering. Ultimately, this principle is about legacy. What kind of world are we building for our children and grandchildren? As the people who literally design and build the world, we have a disproportionately large role to play in answering that question. We have the skills to create a future that is not only technologically advanced, but also environmentally sustainable. It's a profound responsibility to use our problem-solving abilities to tackle one of the biggest challenges humanity has ever faced. Being a great engineer today means being a great steward of the earth. We touched on this a bit when we talked about competence, but it's so important it gets its own principle. Number 7 is all about professional development and lifelong learning. This principle states that engineers have a duty to continuously enhance their knowledge and skills throughout their careers. It's the formal recognition that your education doesn't end when you get your diploma. In a field that changes as rapidly as ours, the day you stop learning is the day you start becoming obsolete. This isn't just about staying competent in your current role. It's also about contributing to the advancement of the profession as a whole. When engineers learn new things, they can develop new techniques, create new technologies, and solve problems in more elegant and efficient ways. This collective growth is what pushes the boundaries of what's possible. It's how we went from steam engines to spacecraft, from vacuum tubes to microchips. It's a virtuous cycle. The profession advances, which creates new things to learn, which in turn fuels more advancement. So what does this look like in practice? It can take many forms. It could be pursuing a master's degree or a PhD. It could mean earning a professional engineer license, which requires demonstrated experience and passing a rigorous exam. It might involve attending technical conferences to hear about the latest research, or participating in workshops to learn a new software suite. It can even be as simple as subscribing to industry journals, reading books, or being an active member of a professional society like ASME or IEE. The key is to be intentional about your growth. This principle also includes a responsibility to help others learn. It's about mentoring junior engineers, sharing your knowledge with your colleagues, and helping to train the next generation. A healthy profession is one where knowledge is shared freely, not hoarded. By teaching others, you not only lift them up, but you also deepen your own understanding of the material. It's about fostering a culture of curiosity and continuous improvement within your team and your organization. In the end, this commitment to lifelong learning is what keeps our profession dynamic and relevant. It ensures that we are always equipped with the best possible tools, both mental and physical, to solve the challenges of today and tomorrow. It's a personal commitment to be better tomorrow than you are today, and a collective commitment to elevate the entire field of engineering. It's about embracing the idea that you will always be a student of your craft. Principle number 8 is about making sure the things we create work for as many people as possible. This is the principle of fairness and equity. It calls on engineers to be mindful of how our designs affect different populations and to strive to create solutions that are accessible and beneficial to all. It's about actively working to avoid discrimination and ensuring that our work doesn't accidentally create or worsen societal inequalities. It's about designing with empathy. For a long time, there was a concept of a standard user, who was often an able-bodied male of average height and weight. Products were designed for this person, and everyone else had to adapt. This principle challenges that notion. It pushes us to think about users with disabilities, people of different body sizes and strengths, and people from different cultural and economic backgrounds. This is the heart of universal design, the idea that products and environments should be usable by all people to the greatest extent possible, without the need for adaptation or specialized design. Consider the simple curb cut on a sidewalk. It was originally designed for people in wheelchairs, but it also benefits parents with strollers, travelers with rolling luggage, delivery workers with dollies, and kids on skateboards. This is a perfect example of equitable design. By solving a problem for one group, the solution ended up helping many others. Fairness in engineering means proactively looking for these opportunities to make our designs more inclusive. It could mean adding closed captions to a video presentation, or designing a tool that can be used comfortably by both left-handed and right-handed people. This principle also forces us to confront potential biases in our technology, especially with the rise of AI and machine learning. For example, if a facial recognition algorithm is trained primarily on data from one demographic group, it may perform poorly and unfairly for other groups. An ethical engineer has a responsibility to question the data, test for biases, and work to make the system fair and equitable for everyone it might affect. We must ensure that our powerful new tools don't perpetuate old prejudices. Ultimately, fairness and equity are about recognizing that engineering decisions have social and political dimensions. The choice of where to build a new highway, the design of public transportation systems, or the development of an automated hiring tool can have profound impacts on social justice. As engineers, we have a responsibility to be aware of these impacts and to use our skills to build a more just and equitable world. It's about asking not just can we build it, but who does this serve and who might it leave behind? And that brings us to our final principle, number 9. It's the one that ties everything else together: accountability and transparency. This principle says that engineers must take responsibility for their work. It means putting your name on your designs and standing by them. If a project is successful, you share in the credit. If it fails, you accept your share of the responsibility, learn from the mistake, and work to make it right. You can't pass the buck. Accountability is the backbone of professionalism. It's the understanding that your decisions have consequences, and you are answerable for them. This is why engineers, particularly in fields like civil engineering, will literally stamp and sign their drawings. That seal is a personal guarantee. It says, "I have reviewed this work, it adheres to professional standards, and I am accountable for its accuracy and safety." This creates a powerful incentive to get things right, because your personal and professional reputation is on the line with every stamp. Transparency is the other half of this principle. It means being open and honest about our processes, our data, and any potential risks. You don't hide problems or sweep them under the rug. If you discover a potential flaw in a design, even late in the process, you have an ethical obligation to bring it to light. You need to be transparent with your team, your managers, and your client about the challenges and uncertainties. This allows for informed decisions to be made by all stakeholders. Think of the tragic case of the Ford Pinto and its exploding gas tank. Internal memos later revealed that the company knew about the design flaw, but made a calculated financial decision not to fix it, weighing the cost of lawsuits against the cost of a recall. This was a catastrophic failure of accountability and transparency. The engineers and managers involved did not take responsibility for the safety of their customers and were not transparent about the known risks. This case serves as a stark reminder of the moral imperative to be open about potential dangers. In the end, this principle is about building trust through ownership. When the public sees that engineers are willing to stand by their work, to be open about their methods, and to take responsibility when things go wrong, it strengthens their faith in the entire profession. It shows that we are not faceless cogs in a machine, but dedicated professionals who are personally invested in the quality and safety of our work. It's about owning your successes, owning your failures, and being clear and honest every step of the way. So there you have it, the 9 core principles that form the ethical foundation of our profession. It's not just about being good at math and physics. Being a true engineer is about being a good human first. It's about using that technical knowledge with a conscience, with a deep sense of responsibility for the impact we have on the world. These principles aren't just a list of rules to memorize for a test. They are a promise we make to society. A promise to be guardians of safety, champions of truth, and responsible stewards of our planet. And look, I get it. In the real world, things get messy. There are pressures, deadlines, and budgets. Sometimes these principles might conflict with each other, and you'll be faced with a tough ethical dilemma. That's where engineering judgment, guided by this framework, comes in. There isn't always a simple black and white answer, but if you always start by putting the health, safety, and welfare of the public first, you'll have a reliable compass to guide you toward the right decision. It's about building a better world, not just building more things. This is the stuff that makes me so proud to be an engineer. We get to be on the front lines of solving humanity's biggest problems, and we get to do it with a code that pushes us to be our best selves. So whether you're a student just starting out or a seasoned pro, I encourage you to think about these principles not as a burden, but as a source of strength and pride. Thanks for nerding out with me today. And as always, thanks for watching.